Welcome back to this lesson on vectors. We are going to do some examples of the addition of vectors. Right, in our first example, we've got a pulling force of 15 newtons to the right and a pushing force of 20 newtons to the right on a box. So a force diagram would look like this. You've got the box, you've got your pulling force to the right of 15 newtons and you've got a pushing force of 20 newtons. Now there's a quicker way to represent these forces, and that is by drawing a free body diagram. Where we reduce the object to a dot and we tie the tails of the forces to that dot. So that would be our 15 Newton force of pull and our 20 Newton force of push. I see that these forces are acting in the same direction, so I choose to the right as my positive direction. We need to get the resultant graphically, so we need a scale, and my scale I'm going to choose 1 centimeter to 5 newtons. Right, so when we have to draw our vectors and add them head to tail, my first vector will be 3 centimeters long. That represents my 15 Newton force, and because the two forces are acting in the same direction, I'm going to add my 4 centimeter vector to that, all in one straight line, and I label the vector the 20 newtons, or F push if you want, and instead of 15 newtons F pull. Then we need to get the resultant vector. The resultant vector will be from the start of the first vector to the finish of the second vector. So we go from there across to there, and we get a 35 Newton as the F net, and it's to the right. Okay, the next method of adding the vectors is algebraically. That's very easy. So it's F net is the F push plus the F pull. It is 20 plus 15, which is 35 newtons to the right. These exercises just puts you into practice for more difficult vectors that comes in grade 11. You'll notice that we work with vectors in one direction here, where you can put these vectors all on one line. So or they go in the same direction or they go in opposite direction. In our second example, we have a force of 20 newtons to the left pulling on a box, while another force of 15 newtons is pulling to the right. So the box, we've got a force F1 of 20 newtons to the right, left, and 15 newtons F2 to the right and to reduce the box to a dot to draw the free body diagram. I've got F1 is 20 newtons and F2 is 15 newtons. Oops, 15 newtons. So graphically means according to a scale. I'm going to use a scale of 1 centimeter, 5 newtons. So to draw this, my 20 Newton force should be 4 centimeters long. So that's my 4 centimeter long 20 Newton. And then to the head of the force in the 20 Newton force, we should draw the 15 Newton force, and that one is 3 centimeters long. So that takes us to that point. This is F2, 15 newtons, 3 centimeters long. Then the resultant is from the start of the first vector to the end of the second vector. Sorry, my lines aren't coinciding there. They're not on the same level, but this is the net force, and it's 1 centimeter long. 1 centimeter long means 5 newtons, and it's to the left. Right, algebraically, to get F net, we're going to say F1 plus F2, but the two forces are going in the opposite direction, so F1 is plus, F2 I'm going to choose as the negative direction, so it's 20 minus 15, which is 5 newtons, and the positive 5 means it is going to the left. It's a resultant vector to the left. Right, let's go to some distance measurements. A soccer player rolls a ball towards a player 10 meters from him. After striking the ball, it rolls 2.5 meters towards the first player. Calculate algebraically the resultant of the displacement. It's always easier if you have a diagram. So here's the ball. It's moving from here 10 meters towards the second player. The second player kicks the ball back and it rolls 2.5 meters towards the first player. So opposite vectors, displacements are vector quantities. So this I'll take as my positive direction. This I'll take as my negative direction. So to calculate the resultant displacement, we prefer an x for displacement. If x net, I will take the first displacement and add the second displacement to it. So I'm going to say that 10 is my first displacement, and then the 2.5 is my second displacement. So it's 10 minus 2.5, and you get 7.5 meters to the second, from the second, the direction is towards the second player. Or you could say from the first player. Now here we have relative directions, and although I chose to the right on my diagram as the positive direction. It's not to say it's going to be to the right, but please don't be confused by that. In the fourth example, a tennis ball is thrown horizontally towards a wall. So let's draw the wall here. And the tennis ball is moving towards the wall with a velocity, which is a vector quantity, 3 meters per second. Oh, they said to the right. After striking the wall, the tennis ball returns to the thrower at 2 meters per second. Now, as the arrows are going in opposite directions, I need to choose my positive direction. It looks like this towards the wall is my positive direction, then away from the wall would be the negative direction. So determine the resultant velocity. Now for number A, to determine the resultant velocity, we use a V for velocity. We can use an R for resultant, or you could use net. It's the same thing, V net. I take the first velocity and I add the second velocity. We could say we take the initial velocity and we add to that the final velocity, with the initial velocity being the 3 meters per second and the final velocity being the 2 meters per second. So adding these, initial is 3, final is minus 2 because we chose minus away from the wall as the negative direction. So the net velocity is 1 meter per second, and the positive answer there means towards the wall. Right, now we get to the tricky situation. B, the change in the ball's velocity. Now this triangle is the Greek letter delta, which we use in science and maths to symbolize change. The change in the velocity is always the final velocity minus the initial velocity, second minus first. So final is negative 2, we chose it as the negative direction away from the wall, minus the 3. So I'm going to get a negative 5 meters per second answer here. And now in vectors, a negative must be changed to positive because the negative indicates a direction away from the wall. So I'm going to say the change in velocity is 5 meters per second away from wall. My time's running out, so I think you can try this one by yourself. Thank you for watching.